Hi, in this video we will learn about series. A series is a finite or infinite sum of numbers. We can write a series in these generic fashions where we have something of the form a1 plus a2, etc. This first series is finite. It stops at the kth term, and we could represent this series using something called sigma notation. We write the Greek capital sigma, and then we write an index that tells us where the series starts. In this case, the subscripts start at 1, and they go 1, 2, up to k. So at the top we write a k, and then a generic expression for each term of this series is a sub n. This notation tells us to start summing up a sub n, where n begins at 1, 2, and ends at k. This is a shorthand notation for a series. The second series is infinite. For this series, we could also use sigma notation. The index starts once again at 1, but now the numbers continue to add up infinitely. So we have infinitely many of these terms that we're trying to add up. Let's look at an example to see how series are useful. Imagine dropping a ball from a height of 1 meter. On each bounce, the ball travels half the height that it did before. We would like to know what is the total vertical distance that the ball travels. Now, this is a little bit unreasonable. We're going to imagine that the ball bounces infinitely many times. It just keeps on bouncing, but every time it bounces, it goes half of the height that it did before. So it would look something like this. And we'd like to know what is the total vertical distance that the ball travels if we assume that it bounces infinitely many times. So we have an initial height of 1 meter. After the first bounce, the ball travels up 1/2 of a meter. So let's think of the distances that the ball travels vertically. Here we have a vertical distance of 1 meter. Then the ball bounces and it goes up 1/2 a meter, then back down. 1/2 plus 1/2, we have 1 meter of travel. And then after the second bounce, the ball travels 1/4 of a meter. It travels up 1/4 of a meter and then back down. So that's a total distance of 1/2 meter. Then we have 1/8 of a meter up, 1/8 down. 1/8 plus 1/8 is 1/4. The next one would be 1/16 plus 1/16, that's 1/8. And so we have this list of numbers, and we're adding up these distances to get the total vertical distance of the ball. So we'd have the initial drop of 1 meter, and then we'd have the bounce of 1 meter plus 1/2 plus 1/4 plus 1/8. The next would be 1/16, etc., etc., etc. If we imagine that the ball continues to bounce infinitely many times, then the vertical travel would be this summation. We could use sigma notation to simplify this. We have 1 plus, and then we have 1/2 being multiplied each time to get to the next number in the series. We can produce this behavior by taking 1/2 raised to the n power, and we start the index at 0. 1/2 to the 0 gives us 1. 1/2 to the first gives us 1/2. 1/2 squared is 1/4, etc., etc. This summation continues to infinity. So this expression represents the vertical travel of this ball. We would like to know, can we find this value? It turns out that we can, and we'll examine what sort of a series this is and see how to evaluate it. This is a kind of series called a geometric series. A geometric series is one in which each term is a multiple of the previous term. In a generic form, we can write a geometric series like this. We have a first term of a, and then each consecutive term is obtained by multiplying by a constant multiple of r. This is called the constant ratio. So we have a times r is ar, multiply by r again, and we have ar squared, ar cubed, etc., etc., etc. This is a geometric series. Each term is obtained by multiplying the previous term by the constant ratio r. It turns out that if the absolute value of the ratio is less than 1, then a geometric series has a finite sum. The geometric series adds up to this value, a divided by 1 minus r. This is the sum. It's an infinite sum that adds to a finite value. It's more useful to think of this formula in the following way. A is the first term. And then we're dividing by 1 minus the ratio. Sometimes textbooks present this formula in a slightly confusing way where it's difficult to determine what the value of a is, what r is. But if we can remember first term divided by 1 minus the ratio, then we can apply the formula. Let's look at an example where we apply this formula. Here we have two geometric series. The first one should look familiar. This is the geometric series from the ball problem. If we were to expand this out, we start at n equals 0, 1/2 to the 0 is 1, 1/2 to the first is 1/2, then we have 1/4, etc., as we saw before. In this example, the first term is 1, and the constant ratio r is 1/2. So the formula tells us first term divided by 1 minus the constant ratio. 1 minus 1/2 is 1/2. We have 1 divided by 1/2, which is equal to 2. This summation represents how far the ball traveled after the first bounce. It was dropped from a height of 1 meter. So if we take 1 meter plus 2, the answer to that bouncing ball problem is 3 meters for the total vertical distance traveled. Let's take a look at this second geometric series. For this second example, it's not clear at first glance that our series is indeed geometric. To check whether it is or not, let's take two consecutive terms and find the ratio. We'll take -4/3 divided by 2. That gives us an answer of -2/3. So to get from 2 to -4/3, we multiply by -2/3. Let's check to see that we have the same ratio between the next couple of terms. Multiply -4/3 by -2/3, and we have +8 divided by 9, which is the third term. Multiply 8/9 by -2/3, and we have 8 times -2, 16, 9 times 3, 27. Yes, indeed, the constant ratio here is -2/3. So for this example, we have a first term of 2 divided by 1 minus the ratio of -2/3. 1 minus -2/3 is the same as 1 plus 2/3. That's 3/3 plus 2/3, that's 5/3. So we have 2 divided by 5/3. If we simplify, this is 6 divided by 5. That is the sum of this second geometric series. Notice, for each of these examples, the common ratio has an absolute value of less than 1. In order to apply our formula, this constant ratio has to have an absolute value less than 1. If the absolute value is greater than or equal to 1, the geometric series would diverge.